Hi everyone, this is your math guru. In this video, I'm going to show you how to solve the following Euclidean geometry using the appropriate circle theorem. Please don't forget to click on the like and subscribe button below for more easy to understand math concept. In the first example, we have in the diagram below, O is the center of the circle, the line AB is the diameter of the circle, CF and EB are chords which meet at D when extended. Chord EC is parallel to chord BF, and the line CO and AC are joined. 1. We are to determine in terms of x the size of F1. 2. Prove that the line DF is equal to the line BD. 3. You have to show that C1 or the angle C1 is equal to the angle C3. And 4, if DF equals to 5 centimeter and OA equals to 6 centimeter, we have to determine the ratio of the area of triangle BFD to the area of triangle AOC. Starting with the first part of the question that says we have to determine in terms of x the size of F1. If we look at the shape as shown, the line AC, CO, OB, and EB, we'll see that angle E is equal to half of 2x. And the reason being, the angle at center is equal to 2 times angle at circumference. That's the circle theorem that applies to that. So we have 2x being twice angle at E. What that means is the angle E is equal to half of 2x, that will be x. Also, note that the cyclic chord CF, B, and E, that's a cyclic chord because all the corners are touching the circle. Then we have the angle E and the angle F1. We have E plus angle F1, that's equal to 180 degrees. That's opposite angle of a cyclic chord. What that means is to find the angle F1, making F1 the subject of formula, we have F1 equals 180 degrees minus angle E, which is the same as x degrees. For the second part of the question, we have to prove that the line DF, as shown, is equal to the line BD. Note that the line CE, I'm going to highlight that, and the line FB are parallel lines such that we have angle B1 equals angle at E. And the reason being that's equal to F because we're able to prove in the first part of the question that E equals to X. So we have that equals to X. And the reason being because CE and FB are parallel lines, therefore B1 and E are corresponding angles. That's because CE is parallel to the line FB. Also, note that the line EC, F, and B, that shape, that's a cyclic chord. Therefore, angle F2 is equal to angle at E, which is equal to x, and the reason being external angle of a cyclic chord, that's equal to the opposite interior angle. So we've been able to prove that angle B1 is x and angle F2 is also equal to x. That is F2 is equal to B1, which is also equal to x. Therefore, the line DF is equal to the line BD, and the reason being that's an isosceles triangle. The base angles of an isosceles triangle are equal when two opposite sides are equal. Isosceles triangle DFB. So we've been able to prove the second point. Going to the third question, we have to show that C1, or the angle C1, is equal to the angle C3. The next question, to show that angle C1 is equal to C3, let's go back to the diagram. I'm going to find my bow tie, angles in the same segment. You can see the bow tie as shown, such that angle A1 or A is equal to the angle at E, and that is equal to x. The reason being angles in the same segment. So what that means is angle A is also equal to x. Also, note that the line OA is equal to the line OC, and they are both radii. I'm going to highlight that. So I have line OC is equal to the line OA, radii to the circle. So therefore, the base angles of the triangle OAC are going to be the same because that's an isosceles triangle. So we have, therefore, angle A is equal to C1 plus C2, and that's equals to x, and that's isosceles triangle OAC. But note that angles C2 plus C3 is also equal to angle F, which is x. I'm going to state that. But angle F is also equal to C2 plus C3, and that's equal to x. We have that as a corresponding angle because we've been able to show that, or it's been given in the diagram, that the lines CE is parallel to the line FB, close bracket. So therefore, from the simultaneous equation that we have, that C1 plus C2 equals to x, and C2 plus C3 equals to x, what that means is C1 must be equal to angle C3. For the fourth part of the question, we had to show that if DF is 5 centimeters, and remember, because the base angles are equal for the triangle DFB, therefore the line DB will also be 5 centimeters, and the line OA is 6 centimeters as the radius, and because OC is also the radius, that will also be 6 centimeters. We have to determine the ratio of area of triangle BFD to the area of triangle AOC. I'm going to draw the two triangles as shown below. So looking at the two triangles as shown, to find the angle at D and O, we have angle D is equal to 180 degrees minus 2x. The reason being, sum of angles in a triangle DBF, the sum of angles in a triangle and up to 180 degrees. Likewise, the angle at O is equal to 180 degrees minus 2x for the same reason. We can also find the angle at O by subtracting 180 from 2x. We can see the line AOB as shown, and the angle 2x and the rest of the angle which you're looking for, that's AOC, will add up to 180. So to find angle at O, that's O2, O2 will give us 180 minus 2x. So the area of triangle BFD, area of triangle BFD, because it's not a right angle triangle, we're going to use half AB sine theta, and that's half multiplying the two sides, that's 5 and 5. So we have 5, I'm going to put that in a bracket, sine of the angle at D, and that's 180 degrees, minus 2x. We'll do the same for the area of triangle AOC. That will be half AB sine theta also, so that's half times 6 times 6 sine of the angle at O, that's 180 degrees, minus 2x. So finding the ratio of area of triangle BFD to the area of triangle AOC, we have, for BFD, we have half times 5 times 5, that's 25 divided by 2, or we can leave it as 25 over 2 sine 180 degrees minus 2x to the area of triangle AOC, half of 6 times 6, 6 times 6 is 36, divided by 2, that's 18 sine 180 degrees minus 2x. Simplifying, we're going to divide both sides by sine 180 degrees minus 2x. That cancels. We are left with 25 over 2 is to 18, and we can have fraction in a ratio. So multiplying both sides by 2, we have 25 is to 36. Note that simplifying from here, we will have had 25 is the same as 25 over 2, because that's in the second quadrant. So we have that as sine 2x. And also simplifying here, we could have had 6 times 6, 36 divided by 2. That's 18 sine 2x. We're still going to have the same ratio of 25 to 36. Let's look at the second example. In the second example, we have in the diagram PSW and WT are tangent to a circle RST at S and T respectively. The line PT is drawn and intersects the circle at R. RS and the line ST are joined. We have RT equals to TS. The angle S1 is X as shown, and TY, T2 equals to Y. Name with reasons 3 angles equal to Y. The line SW is equal to the line TW. That's SW equals to TW. And the reason being, they are both tangent to the circle from an external point. And because the two lines, that's SW is equal to TW, what that means is the angle T2 is equal to angle S3. That's base angle of an isosceles triangle. So we have, therefore, the angle S3 equals to T2, and that's equal to Y. The reason being isosceles triangle SWT. Also, we have angle R2 is equal to Y. That is, we have the angle R2 is equal to Y. That's the tan chord theorem. Remember, we have to find 3 angles equal to Y. So we've found the first one, the second one, we need the third. We have the line RT equal to the line ST. that's given in the diagram. We have that as being equal. Therefore, the base angle, that is, we have ST will be equal to R2, and we've already shown that R2 is Y, so that's equal to Y, and the reason being that's the base angle of an isosceles triangle RST. So we've gotten our three angles, that's R2, S2, and T2 and S3, all equal to Y. Thanks for watching. Bye.